We're going to talk about exponential equations. So an exponential equation, first of all, would be any equation where the variable is in the exponent now. So if you look at this first example here, we're not solving for 3 times x. This is 3 to the power of x minus 5 equals 27. And the first thing we're going to look at is a special case of exponential equations. And this is where the base is equal on both sides. So if we have b to the x equals b to the y, so the same number is raised to a power on each side, then those two exponents would have to be equal too, right? So if the bases are the same, then the exponents have to be the same, right? So if the bases are the same, are equal, then exponents are equal. So we can apply that on this first example here. Now the bases aren't exactly equal right now, right? But what we do know is that 27 is equal to 3 to the third power. And how do we know that? Well, if you don't see 27 and immediately think 3 cubed like your math teacher does, then just, give it a few tries. Like try 3 to the first power, 3 to the second power, 3 to the third power. If you get there, great. If you don't, then you could solve it a different way, which we'll learn later. But for now, we do know that. So another way we could write this equation is 3 to the power of x minus 5 equals 3 to the power of 3. So now we have the same base on both sides, so it has to follow that x minus 5 equals 3. And then, of course, add 5 to both sides, and we would get x equals 8. So example 2 is the same idea, but now notice we've got variables on both sides of the equation, right? But again, let's first look at 125, and a little bit of guessing and checking would reveal that 125 is equal to 5 to the third power. So in solving this, again, I can say that 5 to the power of x minus 4 is equal to 5 cubed to the power of 2x minus 1. Now, on the right side of the equation, I have 5 to the third to the 2x minus 1 power. But then, again, remember that we have this exponent property that says if we have some number, b raised to the x, and then raised to the y, then we can multiply the exponent. So that's b to the power of x times y. So I can apply this property here, right? This would be the same as 5 to the x minus 4. And on the right side, I can multiply those two exponents. So I have 3 times 2x minus 1. And notice it's extremely important that I have parentheses around 2x minus 1, because I don't just want to multiply 3 by 2x. I need to multiply 3 by the entire quantity 2x minus 1. Again, now bases are the same. So I can set the exponents equal. So we have x minus 4 equals 3 times 2x minus 1. And of course, so this is now an easy linear equation. We have 6x minus 3 equals x minus 4. And I hope negative 5x equals negative 3 plus 4 is probably 1. And then we see that x equals negative 1/5. Right, so a couple of more complicated examples. So now you see fractions, and you're like, oh no, fractions. But the thing to keep in mind here is that when we have fractions, we have to remember this rule. If you have something raised to a negative exponent, a to the power of negative x, then that's the same as 1 divided by a to the positive x. Or if we have 1 over a to the negative x, then that is equal to a to the positive x. So how can I apply that here? So I have two bases that look very different, but here I see a 2. So I know that 1/2 to the power of negative 1, or rather 2 to the power of negative 1 equals 1/2. And 2 squared equals 4. So I can see right there, that's going to be my common base on each side. So I can rewrite this equation as 2 to the negative 1 to the power of x plus 2 equals 2 squared to the power of 4x plus 3. And then we distribute, or we bring the exponents down. So really it's 2 to the power of negative 1 times x plus 2 equals 2 to the power of 2 times 4x plus 3. And now that the exponents are equal, I can just solve this equation. So negative 1, or the bases are equal, so I can set the exponents equal. Equals 2 times 4x plus 3. And then we're solving, again, a basic linear equation. So negative x minus 2 equals 8x plus 6. And then I think we get 9x and negative 8. So x equals negative 8/9. And our last example. Here again, the bases look very different, but what you should start recognizing is that 16 and 8 are powers of 2. And of course, it takes a little while to start seeing these things automatically. But again, just a little bit of guessing and checking, especially for right now, since you know that every equation we're going to deal with for the next day is going to be, you're going to be able to solve it with this method. You know that there's going to be a common base. So just try out a few numbers. I'm not a mean person. I'm not going to make you do things like bases of 13 on both sides. So these are both powers of 2. And I know 1 over 16 is going to be 2 to the negative 4. Since 2 to the positive 4 is 16, 2 to the negative 4 is 1 over 16. And 2 to the third is 8. And then here's my equation. So again, using our exponent multiplication property, and this would be 2, 3 times 5x plus 2. So now I can set the exponents equal, now that the bases are the same. So negative 4 times x plus 2 equals 3 times 5x plus 2. And once again, a basic linear equation. I'm really hoping that I'm not making stupid mistakes, because I am too sick to go back and check these things. So 15x plus 6, probably. And then 19x and 14, negative 14. Sure. So x equals negative 14 over 19. So one last thing, when you're finding common bases here, there's more than one way to do it. A lot of times you could do common bases of 2 or 4. Or if you feel like using fractional exponents, I could leave the 16 the same and say that 8 could be 4 to the 3/2 power. And then 16 could be 4 to the negative, or 1 over 16 could be 4 to the negative 2. So looking at that again, I'm saying 1 over 16 is also 4 to the negative 2. And 8 is also equal to 4 to the 3/2. So you could set up this problem using these bases instead, and you'd get the same answer, right? So there's more than one right way to do these problems.